So we'll go back to bits and bytes after we do the flyover, the review. Do you remember the three kinds of errors that we have discussed? Syntax error, the most famous. Another one called semantic, also known as logic. And the third kind, runtime. What's the difference? What's a syntax error? Yeah, program won't even run due to typos. I hate to say or bad syntax because, you know, that's in there. But, you know, typos are bad syntax. Got to come up with a better definition for that. Okay, how about this? A mistake in the grammar of the program. Typos or bad grammar. We know that grammar means syntax, but there we go. Semantic error. What's that? Right. It's freezing, but it tells you to go ahead and wear a tank top. So, program runs, but gives wrong output. And lastly, a runtime error. That's when the program stops running because it hits a situation it does not know how to handle, like dividing by 0 or a disk full. File not found, that kind of thing. Because you could write a program like this, and sometimes it would work and sometimes not. You don't have to write this. This is not a daily. X is equal to input, give me number. X is equal to int x. Y is equal to 1 over x. Print y. There's no syntax errors in this. Hopefully. I mean, maybe I made a typo and I didn't notice. Give me number. 10. 1 over 10 is indeed 0.1. Yay, it's a working program. Now what usually happens is when you test your own program, you make sure it works. You don't try to figure out how to break it. So that's why they have testing departments, you know, in big software companies. But there are several ways to break this program. One is we could type in something like that. Boom, the program blows up with a runtime error. It's a runtime error. It's an error that occurred while running due to perhaps bad input or some circumstance it couldn't control. Like what if Internet Explorer crashed because the web server was down? You tried to access google.com, your network was down, and so IE crashed with all your tabs. You'd be annoyed. That'd be a runtime error. Or if you were working on a Word document and you did a save as, but you typed in invalid character in a file name. You've probably seen that kind of error. And it just blew up, you know. Quit with your thesis, you know, all gone. So you would be unhappy. As you go on, as you become a professional programmer, you'll learn more and more about handling runtime errors. So that's one of them. The other one here is a divide by 0. If I run it and type in 0, it's okay. You know, it's not going to give an error when it converts it to an int, but division, 0 division error. Can't do that. And there's all these sorts of memes about what happens when you divide by 0. Divide by 0. Oh no. Time paradox. I divided by 0. Oh no. I'm changing the language a little bit. Oops, congratulations, your math just destroyed a city. Okay, that's kind of silly, but you get the idea. That's a runtime error. Program stops when it reaches an unexpected state. If anybody else is having trouble with Lucid Chart besides Kathy, please let me know, because that's disturbing. The error she's seeing is that it won't let her edit a document, create a new one, do a download as. It's all kind of pretty odd.
It's mad at me.
Apparently. I don't know what you did to it.
I'm female, it's mad
You,
at me.
you didn't give it cookies.
Dun, dun.
Oh, I'm getting the same error.
Woohoo! Well, maybe it's them, then they must be having.
It must be them. I wonder if they're mad at us for having drawn too many users on our account or
Maybe
something.
somebody had bad math.
Yeah, they divided by 0. I'm going to have to research that. If you have a flowchart drawing assignment, then look, it worked yesterday. I drew that just yesterday. Okay, anyways. Hopefully it's a temporary problem. You have that shape. You have that shape. You have that shape. And one more shape. There we go. Which one do you use for if? If statements. Yeah, the diamond. Which one do you use for process, like assignments and math? Yeah, I'm sorry I didn't delete the words.
It seemed like a trick question.
Right, that's a trick question. You use the Terminator. No, okay. Yeah, math and assignments go in the process block. What does the start and stop go in? The Terminator. And input and output then goes in data. Right. Right. So if I show you a list of shapes like that, just be able to pick which one's which. All right. If you have the idea of, well, if you have things like this, print, radius, float, get the input, and equal sign, and the plus sign. And then your choices were math operator, assignment operator, function, variable. I forgot an important one on the exam. I may throw it in. And keyword. Which one of these is a math operator? The plus. Kind of tricky. You may think equals a math operator, but actually equal doesn't do math. It assigns a value to a variable. So that's called the assignment operator. Equal sign's an assignment operator. That's a math operator along with division and subtraction and all those other fun ones. Which of these, one or more of them, might be functions? Here's a shortcut. Anything with parentheses after it's a function. So, print and float. Those are functions. Why is that a function? Because the parentheses is where you would pass data into the function. You don't pass data into an if statement. You know, you don't do that. So that's not a function. What is radius? Since it doesn't have parentheses, you know it's not a function. So it's a variable, right? You know, radius, x, y, all those things are variables. What about if? Well, that would be a keyword. Keywords are the words that make up the language. We haven't seen a whole bunch of those, actually. But there's DEF, there's if, there's while. Those are all keywords. Alrighty, what's the difference between an operator and an operand? operators are standing by, operands are not. If you have A plus B minus C, which of these are operators? Errorators, operators, and which of these are operands? Well, we already said that a math operator is something like a plus sign. So, what are the operators? Yeah, plus and minus. And the operands are the data that the operators work on, A, B, and C. Also, the whole thing is known as an expression. Alrighty. Remember PEMDAS and all that fun stuff. PEMDAS. What does the P stand for? Parentheses, exponents, multiplication, division, add and subtract. And just remember that these have the same priority, M and D do, and then add and subtract have the same priority. Precedence is actually the correct term, not priority. Meaning that if there are parentheses, those get done first. If there are exponents, those get done before the multiplication and division. Once you get rid of all those, then left to right it's multiply and divides, and then after that it's addition and subtraction. So if you have something like this, 1 times 2 plus 3 to the power of 2, what's the first thing we have to do? Yeah, there's no parentheses, but we got to handle the exponent. You do remember that star star means to the power of 2. So that's the same as, I mean, you would do this in your head or on paper, but that's the same as 1 times 2 plus 3 to the power of 2 is 9. Okay, then what do? What's the next operation we do first? Yeah, we do the multiplication. Not because it's first in line, but because M and D's come before A and S. So 1 times 2 is 2. Gosh, I'm forgetting that we talked about this. Do we know the difference between 3 divided by 2 and 3 / 2? Rounds down. Yeah, this is called floor division.
Oh, yeah, you did. I do remember.
Rounds down.
Where it's 1.1 remainder.
That would be 1.5. That would be 1. And then 3 modulus 2, that's the remainder.
Oh, okay.
And what's, whoops, not 3 modulus 1. 3 modulus 2. What's the remainder? 2 goes into 3 one time with a remainder of 1. What's 4 modulus 2? 0. Why? Because 2 goes into 4 evenly with no remainder. All right, say that you have this. R is equal to input radius. What statement do you add after that to convert it to an int? Right, R is equal to int R. What if you wanted to turn it into a float? R equals float R. Now, if you did it in that order, that'd be kind of silly, because R is equal to int R would round it down, so you've already lost your decimal point at that point. But that's how you convert to an int. And the things with parentheses after them are known as functions. R is the variable. If it has a parentheses after it, it's a function. R is the variable. Oh boy. You know what I'm going to do? I'm going to make that X and Y just for this example for a moment. X is the variable. R is the quote argument, but we haven't really talked that much about methods, so that word argument hasn't come up a lot yet. Also known as a parameter when you write your function. That's known as a parameter. So when I had R is equal to int R, and when I asked you what R was, if you had yelled at me and said, nuh-uh, it's a parameter, you would have been right. But R is a variable, and int and float are functions. Alright, if you have A is equal to, well, let's do A is equal to 1, B is equal to 2, C is equal to A plus B. And then you have name is equal to Lady plus Gaga. There we go. The renowned musician of our times. Here we go. Which one of these is concatenation? If I can spell it. I think that's not right. Concatenation. Alrighty. And which one of these is addition? Right. That's a concat, which means that that's the addition. And don't be fooled. I don't think I put this on this quiz, but if you had this, A is equal to 1, B is equal to 2, C is equal to A plus B, you might think that that equals 3. No. It equals, what does it equal? Well, what do A and B contain? They are concatenated together. So it makes 1, 2. Just like this created the string that said Lady Gaga. Does that make sense? I don't think I asked that one.
You're saying C equals 12? That's what that says? This is 3 question mark no equals 12. Which one equals 12?
Let me choose different numbers. Not that it really matters, but so that they don't all blur together. Here, these are numbers, so when we add them, we get a number as a result. Here we get strings, so it doesn't do math on them. It instead does concatenation, and 4 plus 5 when they're both strings equals 45.
They marry, like Q and U.
Yeah, yeah. Alrighty, when do you use a single equal as compared to a double equal? What's a double equal for? Comparisons. Everybody agree? He is so wrong. Somebody come up with the right answer. I'm totally kidding. It's right. Comparisons. And these are for sets, assignments. Why does that matter? How do you write an if statement? Do you write it like this? If A equals 3? Or do you write if A equals 3 with 2 equals? Which is a better if statement? That one? Yep. If you want to assign the value, name is equal to Joe. Is that correct, or is name equal to Joe correct? The first one. So you can use equal in assignments, in if statements or while statements. Pretty much everywhere else you're going to use a single equal. There's some stuff we didn't get to. Like this. If I give you pixels like that, what number does that equal? But we didn't do that assignment, so we won't do that. A variable has three parts, really. It's got a name, and what else does a variable have? I don't know how many times I've said this. In some classes I repeat it like every day for a while. It's got a name, it's got a type, and then one last thing. I must not have said this every class. Value. That makes sense? So if you have A is equal to 3, what is its name? What is its type? What is its value? Well, its name is A. Its value is 3. What is its type? If it was 3.0, it would be a float. It's an int. XYZ is equal to 3.1. What is its name? XYZ. What is its type? Float. Its value is 3.1. So those are the three parts of a variable. Its name, its type, and its value. That makes sense? Wow, there's a big chunk of the text I'm going to have to cut out. I wonder if last time I did this, I did the exam after spring break so that we had an extra week of material.
No, sir.
Yes, sir.
Is there an in-class assignment today?
No.
Oh, okay.
Good. I was expecting, I thought we were going to have to do something. I was like, oh, great.
You should be typing all these notes in. Should have made you do that. Nah. Wow. I cannot believe that we haven't covered all this stuff.
Let's wing it.
All right, guys. Some of the stuff that we covered on the first day, we're going to recap, which is the idea of binary. When you count a decimal, you do it like this. 0, 1, 2, 3, you keep going. 9, and then you drive your car the extra mile, and what happens? That digit rolls over, and then a 1 is added to that column, right? Then you keep driving, you get to 19. What happens here once we go one more mile? I mean, we know it's 20, but what's going to happen to that digit?
It turns 0.
It turns to 0, and then we add 1 to the next one. So that's in what's known as base 10. We count in base 10 because we have 10 fingers. So binary, computers really only understand two things, off and on. Either you have current flowing through a wire, or you don't have current flowing through a wire. We have a little switch that's on or off. Or you have a bit and a piece of memory in your memory chip, and it's got a magnetized area, or it's not magnetized. Or you have a CD, and it's got all these pits burned into the aluminum, or the gold of the CD, and if there's a pit there, it means a 0, and if there's no pit there, it means a 1. So really, computers do not count in decimal. They only count in binary. Binary is base 2. Decimal is base 10. Deci meaning 10. Can't really think why, but just like hex means 6 and octal means 8, octagons and whatever. Okay, so when if you were driving your car but you were a computer, you drove 1 mile, the only digits allowed in binary are 0 and 1. After we drive 1 mile, we've maxed out that column. So what happens? Same thing that happened here. What does this column become?
0.
A 0, and we carry a 1 over. Now what if we kept going here and we were at mile 99 and we went 1 more mile? This column becomes 0, right? We add 1 to that one, but 9 is the highest in decimal. We can't go any higher. That turns into a 0 and we carry the 1. Okay, so we go another mile. Now we go yet another mile. What happens to that 0? That 1 turns into a 0. A 1 gets added over here. Oops, it already is 1. We've maxed it out. And there, like that. But we can match these up with decimal numbers. A 0 is a 0 in any counting system. 1 is a 1 in any counting system. That's a 2. That's a 3. That's a 4. So, based on that idea, I'm going to pretend that our car has 3 spaces. 001 is the first mile, 010 is the second, 011 is the third, 100 is 4. What would be next? 101, then what's next?
1.
Yeah, we in agreement on that one? And then 111. So if we were going to count these, that's a 0, that's a 1, that's a 2, that's a 3, that's a 4, that's a 5, that's a 6, and that's a 7. So, if you have only one place, the highest value you can count is a 1. If you only have one binary digit. If you have 2 binary digits, the highest value you can count is what? Well, just cheat and come down here and look at what 2 1s in a row means. 3, right. Then if you have 3 digits, the highest value is a 7. There is a mathematical formula that would give that. It's it's n to the power of 2 minus 1, where n is the number of bits. A bit is a 0 or a 1. Bit is the smallest unit of information. Do you have to memorize that formula? No. But it lets you easily calculate. If I had 8 bits, like if I had a good old 8-bit Nintendo, what's the maximum range of colors it might be able to display, most likely? Well, I can just do this. Why are you not popping up? Okay. Google is my favorite calculator. Come on. There we go. So 8 to the power of 2 minus 1 is 63. So counting black, which would be 0, 0, your old Nintendo probably had a palette of 64 colors to choose from, and actually fewer than that on the screen at the same time. Then you bought your Sega Genesis or your Super Nintendo, which was a 16-bit computer, 16-bit machine. It could display from a color palette of 255 colors. If you have a 64-bit video card, it could display 1 of 4,000 colors on the screen. That's not sounding right, actually. That is definitely not sounding right. Yeah, I done goofed. The equation is 2 to the power of n. Now let's do that again, because that's a big difference. 2 to the power of 8 for our old Nintendo. 256. Now that's correct. So your range of numbers are 0 to 255. If you had a 16-bit computer, it's 2 to the power of 16, which is 65536. I've given the example often enough that I have that memorized. So the values are 655, from 0 up to 65535, and so on. So, you know, your PlayStation, I think, was had 128-bit graphics in it, which meant that it could display really nice ranges of colors. Okay, probably didn't even have that. 16-bit colors rather than 18 was 65536. What if you had 32 bits for each color? 4 million. That's about enough. Yeah. That may even be more than 4 million. That's 4 billion? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 4 billion colors on the screen. Definitely enough. So if you had a 32-bit card in it, you know, that's why the PlayStation, among other reasons, had graphics that look so much better than the Super Nintendo, because it had, you know, a video card that supported, you know, 32 bits per color rather than 8 or 16. All right, that's going off the rails a little bit. How could we convert from this to this without just memorizing? What if I had this number, 101, and I had to convert that on the fly? Well, when you're dealing with decimals, you have the idea of places. You have the ones place, the tens place, the hundreds place. That's the ones place, which is actually 10 to the power of 0. A little weird mathematical oddity is that any number to the exponent 0 is 1. You can try it out. Go into Google and type negative 3 million to the power of 0. It'll come out 1. And then you have 10, because we're still dealing in decimals, which is 10 to the power of 1. You have 100, which is 10 to the power of 2. And another little weirdness, or just fact, is that when you're dealing in base 10, that number represents how many zeros there are. 10 to the 1 is 10. 10 to the 2 is 100. 10 to the 3 is 1,000. Right. So if you had a number like this, 1, 2, 3, 4, and you were going to write it out in long form, then this means 4 times 10 to the 0, or you could say 4 times 1, plus 3 times 10 to the 1, or 3 times 10. I'm going to stop doing this. Plus 2 times 100, plus 1 times 1,000. And after we added this up, 4 times 1 is 4, 3 times 10 is 30, 2 times 100 is 200, 1 times 1,000 is 1,000. You add those up, and miraculously you get 1, 2, 3, 4. Big deal. We converted from base 10 to base 10. That's not a big accomplishment. But the idea is the same for base 2. Two to the 0. I really wish I had a good pen. How about this red one? 2 to the 0. 2 to the 1. 2 to the 2. Well, anything to the power of 0 is a 1. 2 to the 1. That's a 2. 2 squared. That's a 4. 2 to the 3. That's an 8. So if we had this number, 0, 1, 0, 1. That means this is the ones column, right? That means 1 times 1 plus, how many times 2? 0 times 2 plus, how many times 4? Yep. 1 times 4 plus 0 times 8. So that's 1. Skip that one. That's 5. So that's 6. And if we go back to our earlier charts, that was it. Whoa. How did I get 1 times 4 is 5? I used to go back to school. There we go. 1 times 4 is 4. Add those together, you get 5. That making sense? Need more examples? Well, open Notepad or Python or something. We're going to type a little bit. I'm just going to make some notation. 8's column, the 4's column, the 2's column, and the 1's column. So 0, 0, 0, 0. That's kind of boring. But that's equal to 0 times 1 plus 0 times 2 plus 0 times 4 plus 0 times 8, which is, miraculously enough, 0. How about 1010? How many 1s are there? Or you could do them in the opposite order. You don't have to start at the 1s. You could start at the 8s. Let's do that. How many 8s are there? There is 1 8. 1 times 8. Plus, how many 4s are there? That's the 4's column, so it's 0 times 4. Plus, how many 2's are there? Kathy's got it. Everybody else agree? Anybody disagree? 1 times 2 plus how many 1's are there? I switched the order of them, and maybe I'm going to rewrite this one in that order. But anyways, 8 plus 2 is 10. Okay, so redoing this in order, I'm not going to redo it. It's all zeros. 0101. How many 8's are there?
You're still using the 8, 4, 2, 1, right?
Right, right.
So 0 times 8. 1 times 4.
Right, 0 times 8. Now we're cooking. Plus 1 times 4 plus
0 times 2. And 1 times
0 times 2 plus
1 times 4.
1 times 1.
You don't add anything that has zeros.
Right, you don't add anything to add 0, so you add the 4 and the 1 and you get 5. After a while, you get used to eyeballing this, and if you had 1 0 1 1, you could say, well, I do have an 8. Do I have any 4s?
No.
I don't have any 4s. Do I have any 2s?
Yes.
I have a 2.
I have a 1.
I have a 1, so that's equal to an 11. All right, guys, for y'all to do on your own, tell me what these are. Those 4 values. Just add them up. I don't care if you do it in the short form like this or if you type out all the zeros and the 1s. So for those who aren't typing, I assume it's because you already got the idea. Alrighty. I may not have given everybody enough time, but most people, I think. What's that first one equal to? Just give me the answer first. That's a 2, yeah. Because it's no 8s, no 4s, 1, 2, and no 1s. How about this one? 6. How about that one? 12. I think I heard somebody say 10. It would be 10 if it was 1, 0, 1, 0. Maybe I didn't. And anyways, what's that one? 9. That's correct. Okay, so that's how you go from binary to decimal. If you're going to go the other way, you pop open a calculator. No, I'm kidding. We're not going to talk about how to go the other way. What you do is you divide by 2, and then if the remainder is 1, then you write a 1 down, else you write a 0 down. Then you divide by 2 again, and you write that remainder down. Then you divide by 2 again, you write that remainder down, and you get it. But to me, this is more important. This concept is way important. Okay, then we have the idea of hexadecimal. And I'm not going to put hexadecimal on the exam. We're going to have to broach this again a little bit more slowly. But the idea behind hexadecimal is if you have 4 bits, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. Well, anyways, by the time you get to 1, 1, 1, 1, what does that equal to? 8 plus 4 plus 2 plus 1 is 15. What if you wanted to be able to represent all of the 4-bit values with a single digit? How is that possible? We only have 10 digits, 0 through 9.
Do a letter?
Yeah, you do letters. And that's called hexadecimal. And although it didn't have to be this, the English people who came up with it decided that the letters would be A, B, C, D, and E, and F. That's 6 extra digits added onto the numbering system. If hexadecimal had been invented in Russia, they have a different 6 front letters, and we'd be calling them something quite different. Let's see if I got that right. That is a 0. That is a 1. That is a 2. That is a 3. That is a 4. That is a 5. That is a 6. That is a 7. And then if you tacked a 1 on in front of all those things, you'd add 8 to them, right? Because if that was a 1 instead of a 0, that'd be an 8. If that was a 1 rather than a 0, it'd be a 9, and so on. So I'm going to cheat and cut and paste. Just change all these to 1s. And so that one's an 8. What's that one?
1, 0.
Let's not do hexadecimal yet. It's an 8 plus a 1, so that's a 9. What's a 1, 0, 1, 0? 10. Obviously, at this point, we stop using our brains and we just look, at that. So this is the binary column, the base 2. This is the decimal. Base 19. That'd be a nightmare. And then this is the hexadecimal. Hex meaning 6, decimal meaning 10, so that's base 16. So the first 10 digits are the same. 0, 1, 2, 3. Here's where doing it in Word would have made more sense. A 10 is an A. An 11 is a B. A 12 is a C. A 13 is a D. A 14 is an E. And a 15 is an F. Yeah, why would you want to do that? Okay, it's so that you could display binary information on the screen more succinctly. What do I mean by that? What if I had this series of numbers? I really want these to be in groups of 4, so I'm going to space it out like this. But but in a computer, they're not spaced out. Computer RAM is just a series of zeros and ones all the way from the beginning to all the way to the end. So, you have a memory chip, and these are the first zeros and ones in it. Let's convert them to decimal, but we're going to totally cheat and just look them up. What's a 1010 in decimal? Well, it's a 10, right? What are all those? What's all that? 15. What's that one? That's a 5. How about that one? 6. And that one? 10. We're back to 10. Okay. So if we wanted to display that as, if you were looking at a cathode ray tube with digits on it, would you want to see a whole bunch of zeros and ones to know what was in the memory? No, you want to see something else. So maybe we take all the spaces out. And we're thinking, okay, that is equivalent to that. Well, that's kind of not really equivalent to that. Why do I say that? Because we don't know whether this is a 10 followed by a 0 followed by a 1, or a 1 followed by a 0 followed by a 0 followed by, a 15 or whatever, We don't know what those are equal to. So I should have used 2 digits in the decimal. Yeah, that was a mistake as well. There we go. So let's rewrite it with 2 digits in every place so that it's all evenly spaced out. Then, when it was displayed on screen, in old-timey computers, there we go. That's a series of decimal values. Those are the first those are the first 4 bits. Those are the second 4 bits. Those are the third 4 bits. Those are the fourth 4. That's the fifth 4 bits, and that's the sixth 4 bits. So we have 6 clusters of 4 bits each. What if we could redo this as binary? Well, what's a 10, in hexadecimal? What's a 10 in hex? It's a. What's a 0 in hex? Well, it's a 0. Anything 9 or less is just the same. What's a 15 in hex? F. What's a 5 in hex? Anything less than 10 is just the same. So it's a 5. What's a 6 in hex? What's a 10 in hex? Yeah, we've already done it, but it's A. Now we don't have any risk. We don't need to space them out with 2 places. We don't need to put zeros in front of some of them. So we could just encode that on the screen as that. 0A, F5, 6A. It took up half as much room. If your monitor is limited to only displaying 80 letters across the screen, or if heaven forbid you were using a Commodore 64 that only had 40, or a VIC-20 that had 22, if you were limited in space, you'd rather display something like this that your mind could then translate into these zeros and ones, if you look at it. And when you work with hex long enough, you get that idea. You get the idea of all these hexadecimal numbers representing bits behind the scene. Now, if the smallest unit of info a computer can have is a bit, memory is actually considered clusters of bits, groups of bits. And I'm sure you've heard the term bytes, megabytes, gigabytes. A byte is 8 bits. Not 8 butts, 8 bits. So really you have all the numbers between 0000, 0000, all the way up to ones, which I will just tell you that in hexadecimal, that's an FF. But you can look at it and see, right? 4 ones in a row is an F. 4 more ones in a row is an FF, is another F. And in decimal, that's a 0, and that's a 255. Converting from hexadecimal to decimal is a lesson for another day. One of the last things I want to do is to show you a site that does something called Hex Editing. Go to Chrome or Firefox or whatever and type Hex, H-E-X-E-D .it. They licensed a domain name from Italy just so it could have the cute IT at the end. Hex Edit. And then do Open File and just go and open up one of your PY scripts. This is what one of your scripts looks like to the computer. Except it's even worse. It's all zeros and ones. But here, this is showing the text that's in your document. Joan Jett, I love rock and roll, put another dime in a jukebox, baby. And it's putting dots instead of spaces for some reason. But most of those are actually supposed to be spaces. And according to whatever coding scheme is being used, which in this case is Ascii, we will talk about Ascii on another day, a D is a hexadecimal 64. An E is a hexadecimal 65. An F is a hexadecimal 66. You kind of get the pattern. 64, 65, 66. We can guess what a G would be, right? 67. So if I come and change that 20, to a 67, it changes whatever that was, a space,
There's a dot.
to a G. So all your files are encoded in bits. Now they all encoded in ASCII, where certain numbers match English letters. No, there would be no reason to encode like an MP3 audio data, or a video file, or an image or something, in anything that looks like that. But for text, it's a one-to-one correspondence if you know which numbers correspond to which letters. And when you're curious about which numbers correspond to which letters, you Google up an Ascii chart. So open a new tab and type in ASCII, A-S-C-I-I, space chart. Then click on images and just choose any one of them. Click view image. There we go. We were looking at a lowercase d. Oh, when I said click any of them, that turned out to be a bad choice. Why? This isn't showing hexadecimal. Let's pick another one. Alrighty, here we go. If I can zoom in on the upper corner over here. A lowercase d is equal to a 64. A lowercase e is a 65. And a lowercase f is a 66. And so if you ever create anything in Notepad, or you ever create anything with the Python editors of whatever kind, or if it's a Word document and you're using English letters, you will probably see these numbers if you hex edited it. I know I put way too many its in there. Edited it. Why are we talking about all this? If you go on and work further in computers as programmers or whatever, you're going to want to have an idea of what's underneath the layer that we see. What we see are words and numbers. But the words are series of characters. And those characters are series of numbers in this or another format. And those numbers are series of bits. So you can kind of see that it's all layered. So what's going to be on the exam involving this? Well, we're going to throw a big chunk of it out until we've done our worksheet on ASCII and hexadecimal and stuff like that. But the smallest unit of information in computer memory that's either a 0 or 1 is called a...
Bit.
Yeah. What is a bit, Alex? Okay, here we go. Oh, and by the way, since they called a byte 8 bits, what's half a byte? A nibble.
Yeah.
I really swear I did not make that up. It's a nibble. Okay, I can't find the other question, but I know what it is. It's going to be to translate a 4-digit binary number to a decimal number. Just like we did. So if I give you 1010, you're going to tell me it's in decimal, not hex. It's an 8 plus a 2 is a 10. Now, I want you all to be able to read this. This is a topic we're going to broach later. If you had a display that could only display black and white, which is quite plausible, you know, like the first Mac in 1985 or whatever, you know, black and white, you know, computers in the 70s or whatever. You see here that we could treat this shape here as a series of 4-bit values. What is a 00001? That's a 1. What is a 0010? What does that translate to? That's a 2. What is a 0100? 4. And a 1000 is an 8. So you could draw any pattern of black and white that fit in a 4 with the letters, you know, with the numbers 0 through 7. No. Because if they were all lit up, if it was 1, 1, 1, 1, if it was an entirely black line, 8 plus 4 plus 2 plus 1 is 15. So we would probably switch over to thinking hexadecimal. But anyways, so you could change. This is what's known as bit-mapped graphics, where the bits map directly onto something that can be displayed on the screen. So in old computers, they didn't do 4x4 blocks. They did usually like 8x8 blocks. And you would have an A drawn there, and you would have a B drawn there, and you would have a C drawn there. Or you might have the shape of a Space Invader, if you remember the old video game Space Invaders. And I know I'm a codger compared to y'all, but space.
I still have my Space Invader.
Yay! Alrighty, like this. You know, that could be bits. Maybe you decide that the blacks are 0s and the whites are 1, opposite of what I just said. You could take this and you could encode it as a series of hexadecimal values. And you would burn that into, you know, the silicon of the Space Invaders machine that you're sending out.
The aliens would think we were stupid if we still did it that way. They're like, what is this?
Yeah, yeah. Well, the poor guy drawing them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I don't know if he had 16 spaces of black and white to draw, or only 12 or something, but you know, he really didn't have a lot in black and white to come up with these things.
Now you look at the graphics now, and they're so realistic.
Yeah,
It's just
yeah,
great.
it's amazing. Okay, lecture over. We have adequately reviewed for the exam. So I will see y'all Thursday.
So,
No in-class assignment or in-class assignment?
If you type this stuff in, just mail it to yourself if you want to keep the notes. I'm not going to bother making an in-class assignment. Yes, sir.
I should.
Okay, you need some help on an assignment? All right. Let me take roll since I'm not asking for an in-class assignment. The next time we talk about this stuff, we will do an in-class assignment, but it'll be a Word worksheet that we fill in, not just typing stuff in like that.